Welcome to our physics experiment, and this experiment is called the Metre Bridge Experiment. What is a meter bridge? If you are joining us in this class, kindly hit the subscribe button so that you'll be notified in subsequent videos. Well, a meter bridge is called a meter bridge because it has a wire fixed in the scale of 1 meter. You can see that this wire is fixed in the scale of 1 meter. In the scale of 1 meter, and that is why we call it a meter bridge. Ordinarily, a meter bridge will have also other components which include the wood. So the wire that you are seeing is made up of an alloy. This wire here, this wire is made up of an alloy. The wire that you can see, it is made up of an alloy. An alloy is nothing but a material like constant tone. It has a constant tone. That's what we refer to as an alloy. It is also good to note that an alloy has a high level of resistivity. So since it is highly resistive material, we use it for this meter bridge. This wire that you can see is fixed. It is fixed on a meter bridge. And the scale is 100 centimeter on a wooden board. So ordinarily, you don't just have the meter rule, you are supposed to fix this meter rule on a wooden block. And that's why I have the wooden block as a source of improvisation in this experiment to show you that we are supposed to fix the meter rule in the wooden block. This is our wooden block. If you look at the wooden block, it has a copper plate. So these terminals that you can see here at some point are called the copper plate. In dealing with the meter bridge, we need the power source. And we are going to be using these cells as the source of our electricity. The power source is made to give us electricity. So we are going to take the positive terminal of the cell and connect it to one end of the meter bridge. We can call it A or we can call it X. When you connect that to the meter bridge, which is on one end of the meter bridge, then you can now connect the other side to the switch. This is our switch. The switch has two ends. You have this end and you have the other end. And we are going to be opening and closing the switch. This is also a switch, but made for more of demonstrations. Students are supposed to use this switch while the teachers demonstrate using this. There is no difference between this switch and this switch. It is all about designs, because here the key is made in a way that it is being fixed, but here the key is made in a way that it is movable, meaning that after our connections, we can close this switch in order to test whether the current is flowing from the cell to the meter bridge. Before we start our connections, it will be important to note what is the purpose of the meter bridge. What is the purpose of the meter bridge? As I state the purpose of the meter bridge, it is good to note that the Metre Bridge Experiment is both high school experiment and university physics experiment. It is high level experiment that sometimes you can do it in Form 4 physics, and you will do it in your second to third year in the university, because the Metre Bridge works on the principle of Weber storm bridge. It talks about the Weber storm bridge, where we are told that P and Q is equal to R and S. And we are going to be using the Kirchhoff's law. So that's why in this experiment, we are going to identify what is our P and what is our Q, and what is our R and what is our S. So the idea is to be able to identify what is R and what is S. Once you have done that, you can identify what is P and what is Q. So if those unknown values are found, you can now determine whether P and Q is equal to R onto S. So that is the Kirchhoff's law, which is done in third year in the university for those doing physics. And in high school, we use it because it also talks about how to calculate the unknown resistance of the wires. And we are going to be using the resistance box. Before I talk about P and Q, let's talk about R and S. So what is R and S? Now I will take you to the resistance box. What you see here is called the resistance box. This is our resistance box. The resistance box contains varying ohms. So at each of these terminals that you can see, ohms are being varying. So we have 1 ohm, we have 3 ohm, we have 5 ohm, up to 30 and above, depending on the size of the resistance box. Those ohms that are varying are being connected to the copper plates of the resistance box. So all these varying ohms we use the copper plates in order to fix it on the meter bridge. You can see the meter bridge. We have those copper plates, those terminals. So we are going to connect the resistance box varying ohms. If we take 1 ohm, for example, we can connect two ends of the resistance box to the meter bridge terminals, which is those copper plates. And then we are going to see how they are deflecting on the galvanometer. Now, what is S? We have already identified what is R. It is the resistance box. Our S is nothing but the unknown resistance that we need to calculate. So students usually are confused on what is S. This spring represents S. This is always S. It is the unknown resistance that you must calculate. How do you calculate the unknown resistance? Connect this unknown resistance, which is the spring, to the meter bridge. We are going to connect the two ends of the unknown resistance, which is our spring in this case. We are going to connect them to the meter bridge and therefore vary our connections as we take the records. Now, how do we take the readings? For measurement, we are going to use galvanometer. I know all this while we've been using voltmeter and ammeter. But in this case, we are going to use our galvanometer. Galvanometer has a central scale. This is different from ammeter and voltmeter. Take for instance, if it was voltmeter, the scale reading will start from 0 and the deflection is supposed to go up. If it was ammeter in this case, you will see ammeter, the scale reading will start from 0 and it's also supposed to deflect upwards. But in this case, we are going to use galvanometer because it has a central scale. When you go left, it has 30 milliamperes. And when you go right, it also have 30 milliamperes. So we are going to be measuring 30 milliamperes to the right and 30 milliamperes to the left. So we are going to use the galvanometer in this meter bridge experiment. So you are going to take your meter, the galvanometer, and connect to one end of the meter bridge, as indicated on this diagram. Once we have connected one end of the galvanometer on the meter bridge, as shown, we are now going to take our jaw key. This is the jaw key. What is a jaw key? A jaw key is nothing but a connector. So we are going to use this jaw key connecting one end of the galvanometer as we are going to measure how the galvanometer are going to be deflecting, if we go right or if we go left. And the idea is to be checking whether it is deflecting right or whether it is deflecting left. Now finally, what is P and Q? Remember we had those unknown values R and S. Then we have P and Q. So what is P and Q? Once the deflection happens left to right, the P and Q must be equal to R and S. Now, after your connection, you will be variating your meter bridge using the jaw key. The point of null deflection, is that point where the galvanometer is no longer moving right or left. If the galvanometer is no longer going right and is no longer going left, we say that the galvanometer is at 0 point. That point is called P. So it is the point of null deflection. The point beyond null deflection is the point Q. And you will see that after our connections. Because you are going to see that as we start from 1 going forward, at some point the galvanometer will no longer move forward. From my previous experiment, I see that 43.5 is the point of null deflection. So in your case, if that point, the point where the galvanometer is no longer moving right or left, you record it as the point P. And the point, if it is 43 that you have recorded as null, beyond 43, let's say point 43.5 or maybe point 44, all those points you have there is now going to be point Q. So the idea is that now that point P and point Q, which is the point of null deflection and the point beyond null deflection, is equal to point R and S. Already we know what is our R. R is the resistance box as we variate ohms. And S, we had used our spring balance as the unknown value that we are calculating. So that R and this S must be equal to that point of null deflection, which is point P, and the point beyond null deflection, which is point Q. Remember that resistance is directly proportional to the length, meaning that the resistivity is the same. It means that the area or the cross-sectional area also must be the same. And once we are done with this experiment, we will therefore establish that L, which is the length, and S are directly proportional, meaning that if P and Q is equal to R and S, therefore L and S is equal to 100% minus L, which is the length of the wire. From this, we are able to calculate the unknown resistance of the wire. And that is how the meter bridge works. The next thing that is left in this video is to show you how you can do the connections. Now, let me show you how you can connect your meter bridge. From the negative terminal of the battery, connect the negative terminal of the battery. You must know which side is the negative terminal. To X or A, which is the one end of the meter bridge. So you do that connection. From the other end, which is the positive terminal of the battery, connect it to the switch, to the one end of the switch, as you have seen. So let's connect this. From the other end of the switch, which is going to be negative now, connect it to the other end of the meter bridge. Connect this to the other end, which is B. If the other one is A, this is B, or you can call it Y if the other one is X. Now, go to the galvanometer. From the negative side, of course, we know that galvanometer has no positive or negative. It is having a central coil. So just connect one end of the galvanometer to the other end of the meter bridge. And then connect your jaw key, one end. You have your jaw key. The next thing that you need to do now is to check if the connection is working. You can see that it is working. The galvanometer is deflecting. Now we can connect our resistance, the unknown resistance, R. One end of the resistance R, we connect the other end also to the meter bridge. And finally, what is remaining now is the resistance box. So if you have the resistance box, this is the resistance box. You simply connect one end of the resistance box to the meter bridge and connect the other end of the resistance box to the meter bridge. The resistance box will help you to know how the galvanometer is deflecting. For instance, if you remove 1 ohm in the resistance box, maybe you take 5 ohm, the galvanometer will show you a different deflections. And those deflections are what you will be recording. And I told you at the right, it is going 30 milliamperes. At your left, it will also go 30 milliamperes. And this is how the meter bridge experiment works. So in the next video, I will be taking you to the board in order to show you how now you can do computations that involve meter bridge experiment. Hope you have enjoyed the video. Do well to subscribe to this channel and see you in the next video.